waves. You guys are definitely going to want to take notes, especially on the terminology here. There's going to be a lot of new terms for you guys to learn. So you guys need to know the term wavefront and the term ray. You guys may have seen, or almost certainly will see in the future, waves drawn like this. And then you'll be labeling the different parts. Like the top up here is called the crest. And the bottom down here is called the trough, and so on. We're not getting to those terms just yet, so this is not going to be helpful for these terms. Pretty much rather than a cross-sectional view of the wave here, you need to be looking at the wave as a whole. So a wavefront is not just the point at the top of a wave. It's if you have a three-dimensional wave, it's every point at the top of the wave all connected in a line. So that's a wavefront. And then if you draw a line perpendicular to the wavefronts, that is known as a ray, and that shows the direction that the wave is traveling in. So if you have straight waves like this, the rays will be perpendicular, or if you have circular wavefronts like this, then the rays will diverge. So a bunch of terms here. Reflection. Like I said, with the tank of water, you have a wave going through the tank, and then it hits the edge of the tank, it's going to reflect off of it. Basically the wave bouncing off of something. Transmission, like I said, if you have a little spill of oil inside of the tank, as the wave goes through the water and enters the oil, that is a transmission from one medium into another. Absorption, I'll give you a theoretical example. This isn't actually how it works, but if, again, we have the tank of water with the oil in it, if when the wave went from the water into the oil and then the oil kind of contained it, collected it, and didn't let it back out into the water again, that would be an absorption. Yeah.
Well, we were talking about any kind of wave, right? Radio waves, sound waves.
It sounds like you guys are mostly going to be working with like mechanical waves, like water waves and stuff like that. Sound technically is a mechanical wave. Pretty much what happens when you make a sound is your vocal cords are vibrating the air, and then that vibration travels through the air as a wave.
So, about radio waves, though.
Radio waves are a type of electromagnetic wave. It's the same thing as light. Light is an electromagnetic wave, as are radio waves, as are microwaves, as are a bunch of different types. They just have different wavelengths. So radio waves have wavelengths that are this big. Radio waves are like that. Light waves are a millionth of a millimeter or something like that.
What's the medium if they're in space?
Mechanical waves cannot travel through space. Space is a vacuum, there's nothing for them to travel through, which is why there's no sound in space. In space, no one can hear you scream. You know? So a mechanical wave, like water or sound, obviously can't travel through space, but electromagnetic waves, like light or radio waves, can. And that's because they are their own particles, basically. Like, light is made up of photons. Those particles, those photons, just act like a wave. It's the wave-particle duality. It's complicated, but apparently you guys aren't learning about electromagnetic waves. You guys are just doing mechanical waves, so don't need to worry about it. All right, refraction is when the wave bends due to a change in speed caused by the density of a new medium. So, a really cool example of this is, say you are standing on the Earth right here. The Earth has an atmosphere of air around it, and then it's empty space, and then say it looks to you like the sun is right here. You see the sun, it appears to be right there if you were to draw a straight line. But what happens is when the light comes from the sun, it's traveling through the vacuum of space, there's nothing there, really, really fast, and then it hits the atmosphere and it gets bent slightly because air is a lot more dense than nothing. So the light is going to bend. So what's actually happening is the light is coming from over here. When it hits the atmosphere, it gets bent into your eye like that. So when it looks like the sun is over here, the sun is actually right there. So like when you see the sun at the horizon during sunset, it looks like the sun is right over the horizon, but since the light is getting bent, the sun is actually a few degrees below the horizon already.
That's cool.
So, the law of reflection. pretty much just says that the angle of incidence is going to be equal to the angle of reflection. What that means is, you guys are actually probably familiar with this already just from your daily life. Imagine you have a pool table, okay? So, you have a pool table like this. There's a pocket here, a pocket here, pocket here, pocket here, and so on. But say you have your ball that you're trying to get into a pocket right here, but there's a ball blocking this pocket and this pocket and this pocket, for example. You can still try and get it into this pocket by bouncing it off this wall, right? But where along the wall do you want to hit such that it will bounce into the pocket?
Probably one of those like
So
dots.
let me give you some reference here. So which of these tick marks are you going to want to hit such that it bounces off and into the thing?
The middle.
Middle one, right? Because
I feel like he's a pool
it makes sense to you, hopefully, that I'm going to draw a normal line, a line perpendicular to the surface that it's going to reflect off of. You guys probably intuitively know that if you bounce the ball here, it's going to bounce off at the same angle. This angle is going to be equal to this angle.
Are you a pool shark, Mr. Marco?
Not exactly, but I'm probably better than someone who doesn't think about this type of thing, because this isn't actually how pool works. If you've ever played, you know that you hit a cue ball, and that has to hit another ball, and you're trying to get that other ball into a pocket. So, as a more true-to-life example, say this is your cue ball, and you're trying to hit this ball. If you hit kind of on the side of this ball here, you can make it bounce this way off of the opposite side somewhere and in. Now, where do you want to hit? Do you still want to hit that same middle tick mark there? Yeah, exactly. If you hit this same tick mark,
Yeah, he's probably.
now that it's not coming in from this angle, it's coming in from this angle, it's going to bounce off at an equal angle and going to be nowhere near that pocket there. So if you're trying to hit this pocket here, you need this angle to be a little more acute. You want to hit it somewhere around, let me get rid of that. You want this ball to hit maybe somewhere around here, such that this angle matches this angle and it goes nuts. So that's pretty much all it's saying, that the law, or the angle of incidence, which is this angle from the normal line to your ray, is going to be equal to this angle from the ray off of the other side of it. So this is fixed end reflection. The situation here is pretty much, this is like a bungee cord, and you have it tied to a post over there. If you flick the bungee cord such that a incident pulse is going up above, like the plane of your bungee, when the wave travels along and hits the fixed end here, the reflection is going to be down below the plane of your bungee. It's pretty self-explanatory. Phases of a wave. You've got a wave here and particles traveling along the wave. If you have two particles at the same spot on the wave, like say they're both at the troughs or both at the peaks or both at anywhere, as long as they correspond to the same area on the wave, then the wave is said to be in phase. If they aren't at the same spots, as long as they're not at opposite spots, it's considered out of phase. So if you have one here and one not quite at the peak, or one here and one here or something, those are out of phase and they'll have a different displacement. And they may or may not be moving in the same direction, because right now this one's instantaneous velocity is pointing this way and this one's instantaneous velocity is pointing this way, so they're not traveling in the same direction. A wave is in opposite phase when they are at the exact opposite spots, when you have one at a peak and one at a trough, or one at a trough and one at a peak. Those ones may or may not be moving in the same direction, because right now this one's instantaneous velocity is in that direction, as is this one. But once this one moves to here, its instantaneous velocity will be this way, and this one's over here and will be that one. Like you guys saw in that video that I showed you, two waves can interfere with each other.
Yeah, superposition.
Yeah, and so pretty much the result of that interference is the superposition. So like when he was doing those two balls and you saw those lines where the waves canceled each other out and there was no wave at all, the superposition of those waves at that point was zero because the trough met up with the peak and they canceled each other out. So the superposition was zero in those spots. And then there's two different types of interference. There's constructive and destructive. What I just described, where the peak meets up with the trough, they'll cancel each other out. That's a destructive type of interference. But if a peak meets up with a peak, then those two will add together and create a larger wave. And that's constructive interference. So the last one, law of refraction. Again, when a wave is traveling from one medium into a different medium with a different density, it's going to get bent a little bit. So if you're standing over a pond or something and looking down into it, light is going into the pond. As long as it's not coming in perfectly perpendicular, it's going to get bent. So you might expect it to keep traveling in the exact same direction, but it's not going to. You guys think it's going to go more off this way or more off this way?
Yeah.
Right. You can kind of go like that. A good way to think of it, the way my physics teacher taught me to think about it, is rather than thinking of, like, in the case of light, it's a particle, a point particle. Rather than thinking of it as a single point, kind of think of it as two wheels connected by an axle. So if the two wheels connected by an axle are coming in and then it hits something more dense, this wheel is going to hit first and kind of cause this wheel to swing around more, and it's going to go in at an angle like that. So that's how you know it's going to get bent down as opposed to getting bent up.
Oh, that's why when you look at your hand underwater, it looks like
Yeah,
it's like broken.
yeah, exactly. So like a cool consequence of this, very related, is that say it looks to you like there's a fish in the water right here. The fish isn't actually right there. The fish is over here. So like if you're on a desert island or whatever and you're hunting for fish, if you stick your spear in and try and hit where you see the fish is actually at, you're going to miss it. You're going to go in over here and miss the fish. You need to aim a little bit below where the fish appears to be. You can totally see, like if you're just at a pool or whatever and you stick your hand in, like she was saying, your hand doesn't, your hand looks like it's getting broken. It's going off down this way instead of straight. And then this equation here is very important. Not only does the light or the wave or whatever get bent, the speed also changes. If this is light, it's traveling a little bit faster through air than it does through water. And so the relationship here is the sine of angle 2, this angle right here, over the sine of angle 1, this angle right here, is proportional to the velocity 2 over velocity 1. So pretty much they might tell you how fast it was going at first, how fast it's going afterwards, and the angle of incidence, and then you'll have to find this angle of reflection. Or maybe they'll give you the two angles and one of the speeds, and you got to find the other speed. Just plug the three variables that you know into this equation and solve for the other. So that is pretty much the
That was
introduction
it?
to wave behavior. Yeah.